So in this video, we're going to talk about changes to the exponential function in the values of a, as opposed to the values of b, like I did in the last video and like we did in class. So this is right where we left off. We can see the parent function there, the domain and range of the parent function, and then the equation form that we're using, a times b to the x. One of the ranges we used in class today for values of b was for values of b between 1 and 2. So here's an example, 1.2 to the x, and let's compare that to the parent function. Here you can see 2 to the x, and now here comes 1.2 to the x. Notice how that value of b between 1 and 2 is above the parent function for negative values of x, and then below the parent function for positive values of x, and then intersects at the same spot, y equals 1. These are the sort of observations I'm looking for. And you can see the same thing in the table. There's the y-intercept, the same value. Here are positive values of x. Notice how the parent function is increasing much faster than 1.2 to the x. And now if you look at negative values of x, notice how the parent function decreases much faster than 1.2 to the x does. That should give you a sense of how the value of b is changing the overall behavior of the graph, specifically when the value of b is between 1 and 2. If you're wondering how I got my window to look like this on the graph, there is a button for window, and I've set the x minimum to be 5, the x maximum to be 5, the y minimum to be negative 0.1, so just below 0, and the y maximum to be 5. That way I can see a little bit more of the graph. I could just as easily have set it to negative 1 to 5. Let's let the y minimum just be 1, and maybe let the y maximum be 10, and then look at the graph. This is a less useful window, but it gives you more control over which part of the graph you see when compared to the zoom features I showed you earlier. Now for the value of a, which is what we'll be exploring in class tomorrow. Let b equal 2, so we're left with the parent function 2 to the x, and then let's try different possible values of a. In the video, let's just do what happens when a is greater than 1. And we'll explore other cases in class tomorrow. Here's our calculator. Y equals, there's our parent function. And this time, we will leave the parent function alone, but multiply, let's say, by 5. There's 5 times 2 to the x. And let's graph. So my window's out of whack. I'll just reset it to standard with the zoom. There goes the parent, and there goes the value of a. Taking off much more quickly. So we want to get a sense of what's changed. Let's fiddle with a window. We don't need any negative values of y, so I can set that at 0 or just below 0. The y max at 10 is fine. And let's scoot everything to the left some. There goes 2 to the x, intersecting the y-axis at y equals 1. Here comes 5 to the x, intersecting the y-axis at y equals 5. Here's the table. Table set. Let's start from 0, count by 1. So you can see the y-intercept has been shifted up to the value of a, and then every point has been multiplied by 5, which makes quite a lot of sense and helps us make a prediction. If I change this 5 to a 4, what do you expect the y-intercept to be? Notice how every point on the parent function has been multiplied by 4. This should help you draw a conclusion about what happens when the value of a is greater than 1. In class tomorrow, we'll want to look and see what happens when the value of a is between 0 and 1, when the value of a is negative, and then see if we can draw some conclusions about what we've learned.